Welcome to this video on the oxygen-haemoglobin dissociation curve. The oxygen-haemoglobin dissociation curve is a graph relating the percentage of hemoglobin saturated with oxygen to the partial pressure of oxygen. Arterial PO2 is 13.3 with a hemoglobin saturation of 97%. It is not 100% due to venous admixture constituting physiological shunt. Venous PO2 is 5.3 kilopascals with a hemoglobin saturation of 75%. P50 is 3.5. This is the PO2 at which hemoglobin is 50% saturated, and it is the conventional point used to compare the oxygen affinity of hemoglobin. Now we can go on to discussing the shape of the oxygen-haemoglobin dissociation curve. Firstly, allosteric modulation. When oxygen binds to hemoglobin, the two beta chains move closer together and change the position of heme moieties that assume a relaxed, or R state. When oxygen dissociates from hemoglobin, the reverse happens and the heme moieties take up a tense, or T state. Secondly, cooperative binding. When oxygen binds to hemoglobin, the R state is favoured, which has an increased affinity for oxygen and so facilitates the uptake of additional oxygen. The affinity of hemoglobin for the fourth oxygen molecule is therefore much greater than that for the first. Next, we will go on to discuss what are the major physiological factors that determine the position of the curve. When the curve is shifted to the right, this facilitates the unloading of oxygen into tissues, and the P50 value is higher than 3.5 kilopascals. Factors that shift the curve to the right: reduced pH or increased hydrogen ion concentration, increased temperature, increased 2,3 dpg, anemia, pregnancy, post-acclimatization to altitude. Now we will discuss factors that cause the curve to be shifted to the left. Increased pH or reduced hydrogen ion concentration, a decrease in temperature, decreased 2,3 dpg, decreased PaCO2, methemoglobin, carboxyhemoglobin. What is the Bohr effect? The Bohr effect. This describes the right shift in the curve in association with increased PaCO2 and hydrogen ion concentration. What is the double Bohr effect? This refers to the situation in the placenta where the Bohr effect operates in both the maternal and fetal circulations. The increase in PCO2 in maternal intervillous sinuses assists oxygen unloading. The decrease in PCO2 on the fetal side of the circulation assists oxygen loading. The Bohr effect facilitates the reciprocal exchange of oxygen for carbon dioxide. The double Bohr effect means that the oxygen dissociation curves for maternal hemoglobin A and fetal hemoglobin F move apart, i.e. right shift maternal and left shift for the fetus. What is the Haldane effect? This describes the increased ability of deoxygenated hemoglobin to carry carbon dioxide. Conversely, oxygenated blood has a reduced capacity to carry carbon dioxide. The Haldane effect occurs because deoxygenated hemoglobin is a better proton acceptor than oxyhemoglobin. Thank you for watching this video.